All right, so now what I want to do, now I will be solving the wave equation, which is what I said I was going to be doing in the previous video, but I did something else instead. So this is the wave equation, or in one dimension, I sometimes call it the string equation, since I think about it modeling the vibration of a one-dimensional string. So here we're going to look at the PDE. It's going to be the double t derivative of u is equal to the double x derivative of u. So it's the same PDE that we saw before. And our initial conditions, our boundary condition, I'm going to write those next. We're going to assume that u of 0t is equal to u of 1t, and these are both equal 0. So this corresponds to having a string pinned down at location 0 and location 1, and then we want to plug it to see what happens. Now, our initial conditions, just like we saw in the infinite case, u of x 0 is equal to f of x. And since it is a second order equation in the t variable, we also need to know the initial velocity. So u of x 0 is going to be equal to g of x. Okay, so that's the setup. And just as we have been doing, we are going to find, look for solutions of the form u of xt, u of xt is equal to h of t times phi of x. Sorry, my sister just came by. Okay, so u of xt equals h of t times phi of x, and now we are going to plug it into the PDE to see what we can determine about h and phi. And again, the reason that h is going to be this function and phi is going to be the, the reason that x goes with phi or phi goes with x is that the boundary conditions are for x values. All right, so if we plug this into the differential equation, on the left-hand side, we have h double prime of t times phi of x, and on the right-hand side is going to be h of t times phi double prime of x. We're going to do the rearrangement that we did before and get h double prime of t over h of t is equal to phi double prime of x over phi of x. Similar things to what we saw in the case of the heat equation, just a function of t, just a function of x, and so this has to be equal to some constant that we're going to call minus lambda. And it's minus lambda for the exact same reasons that it was minus lambda in the previous ones. Now, for the phi equation, what do I get? This is just phi double prime is equal to minus lambda phi, and what are the boundary conditions? Well, they're 0, so it tells us phi of 0 equals phi of 1, and they're both equal to 0. So I know now that phi k of x is going to be equal, this is like the first heat equation that we looked at, phi k of x is going to be equal to sine of k pi x. So I know we're going to get sine of k pi x. So now I'm going to look at the h equation. So what am I going to get for the h equation? Well, I'm going to have h double prime is equal to minus lambda, which is k pi squared. Just all of this is from the video on the heat equation. H double prime is equal to minus k pi squared times h. So what is h? Well, h of t then is going to be equal to some constant times cosine k pi t. Remember, h is the t equation, plus b times sine of k pi t. So now our product solutions are going to be a little more complicated. We're going to have uk of xt is going to be equal to, let me write it like this, is going to be equal to ak cosine k pi t plus bk sine k pi t, and all of this times sine k pi x. So those are our product solutions. Okay, just step out of the way here for just a second. All right, so now what we're going to get, well, again, we're going to go back through this whole thing again. If we plug in t is equal to 0, so there's a little, more steps here, but we want to know in what sense is this going to be a solution to this differential equation, or to this entire problem here. Well, as we saw before, we're very similar to what we saw before. It's going to satisfy the PDE because each term satisfies the PDE. And it's going to satisfy the boundary conditions because if you plug in x is equal to 0, and if you plug in x is equal to 1, you're going to get 0. So this function satisfies the PDE. The boundary conditions, does it satisfy the two initial conditions? Well, if you plug in t is equal to 0, you get, if you plug in t is equal to 0, you get ak times sine of k pi x. So if f of x happens to be equal to sine of k pi x, then it's going to satisfy this initial condition. And if you take a derivative, which I'm going to do now, if you take a t derivative, because we're going to have to use this in just a moment. Okay, I'm going to write it down here because I'm obviously not going to have enough room. If you take a derivative here, we're going to get minus k pi ak sine of k pi t plus k pi bk cosine k pi t, and all of this times sine of k pi x. Okay, so now if you plug in t is equal to 0, you get k pi bk times sine k pi x. And so if g of x happens to be equal to that, then this is going to satisfy that equation as well, or that initial condition as well. Well, as you can probably suspect, just like we did for the heat equation, we're going to say u of xt is going to be equal to the following sum. I hope I have enough room here. We're just going to add up all of these uk's. So k equals 1 to n. We're going to have ak cosine k pi t plus bk sine k pi t, and then sine k pi x. Sorry. Again, all we're doing is we're just adding up all of these k's from k equals 1 to n, or all of these uk's for k equals 1 to n. Okay, now the question is, in what sense is now this a solution to this problem? Well, as before, it satisfies the PDE and the initial conditions. We just need to understand in what sense does it satisfy the initial conditions. Sorry, I think I said it wrong. It satisfies the PDE and boundary conditions. We just need to know in what sense does it satisfy the initial conditions. Okay, so if you plug in t equals 0, you're going to get the sum k equals 1 to n. Again, if I plug in t is equal to 0, the cosine part is 1, the sine is 0. So this is going to be ak sine k pi x. Okay, well this is good. We know how to handle this if we choose ak to be equal to 2 times integral from 0 to 1 of f of x times sine of k pi x dx. Then in the case where f of x is exactly equal to a linear combination of sine functions, this is going to be exactly equal to f of x. But in the case, the more general case, the more realistic case in which f of x can only be approximated by a linear combination of sine functions, this choice of ak gives us the best approximation. Okay, now similarly, I need to see what happens when I take a derivative. So the t derivative, u of x is 0. Well, what's going to happen? I'm going to have the sum k equals 1 to n. Okay, this is the u derivative. So if I look over here and plug in t is equal to 0, sorry, the t derivative, If I look over here and plug in t is equal to 0, this term goes away, and all I'm left with is k pi bk, because this is 1, bk times sine of k pi x. And I want this to be equal to g of x. Well, if I pick bk, if I pick bk to be equal to 2 over k pi times integral from 0 to 1 g of x sine k pi x. Okay, so if I pick bk to be 2 over k pi, really what I'm saying is I want k pi bk to be equal to 2 times this integral, but I want to solve that for bk, so I get this. So if I pick bk to be 2 over k pi times integral from 0 to 1 of g of x sine of k pi x, if g happens to be a linear combination of sine functions, then this is going to give me an exact solution. This is going to be exactly equal to g of x. Whereas, on the other hand, if I only know that g of x is approximately equal to a linear combination of sine functions, these bk's are going to give me the best approximation. So at any rate, up to what we know how to do so far, this is going to be the best solution that we can possibly get using the method of separation of variables. And as I've said again, and as I've said before, and I will say again, we're going to see that actually we can replace in, if n equals infinity, we can actually show that most functions can be equal to a series of these sine and or cosine functions. But this is just going through the method of separation of variables for a different differential equation like this.